Hello everyone, this is my SAR ADC R2R ladder DAC. Here we can see the R2R ladder hooked up to 7 switch banks, going up in fractional voltage amounts, all the way up from 0 volts to 5 volts. Next, we can see the LF398 working as we adjust a potentiometer value, and as we click the sample value, it responds with what the potentiometer is showing, as seen right here. Lastly, we can see when we read the sample and holds value on an op amp along with the R2R ladder's voltage value on an op amp, the output is being compared and the output is being shown on the DMM right now. Now let's get into how the circuit works. The two steps in understanding how this portion of the circuit works are understanding how the LF398 sample and hold IC functions and how the R2R DAC ladder functions. For starters, we're going to talk about the DAC ladder. The DAC is a resistor configuration that is able to divide the current values so that over here on the MSB side, the current has half of its voltage flowing to the output while half of it is flowing into the rest of the circuit flowing to ground. Now, the exact configuration of this by using principles such as the Thevenin's equivalent circuit principle and the superposition principle mean that as you go further and further down into the circuit, further away from the output, it becomes more difficult for the current division to equal half, and it linearly decreases, where here, MSB, it's V over 2, at the next, it's V over 4, and at the next, it's V over 8, and this continues by a power of 2, just how we'd expect binary bits to function, creating a digital to analog converter. Now on the other side, we have the LF398. This is a simple functional block diagram of the LF398 to help you understand how it works. Here we have the input, which is the analog input, and here we have the logical input, which is a rising edge along with a logical reference. The logical input provides the role of setting a rising edge that will trigger this switch, which in most circumstances will be a FET chip or a BJT. And as this is going on, we also have an input signal, which is taking an analog input through an op amp, which only impedes to make sure there's no current losses. As it flows through this rectifier, and if the logic reference is high, will flow through this second buffer right here, which has the signal flowing through a hold capacitor, which is slowly discharging the signal and will slowly decrease. Now, as I said, the way the circuit functions is it's taking the input voltage, flowing through this portion as it reaches the secondary op amp, before reaching the output point where it will be slowly discharging as the capacitor's input voltage, which is now holding the input, once the logical reference is no longer there, it will slowly discharge, creating the LF398 IC. One last key point to mention about the op amp used here is that although 1, 2, and 3 are the desired pins, this is a dual op amp IC, so there's a secondary set of pins that will provide the exact same function. As well, on the power supplies, it is requiring here positive 9 volts and negative 9 volts. This is an allowable operation when connecting the positive end of one power supply to the negative end of the other power supply. And the negative end of the power supply where the positive end is connected to the ground will now provide a negative 9 volts, as voltage is always relative. One last key point to mention is that for the LM393, it's an open collector op amp, which means its output needs to have a 5 volt pull-up resistor to get the desired output.